Hello. In this lecture, I didn't plan to start chapter 7, but the lecture was too short. So I decided to introduce what we are going to do in chapter 7 for the remaining 10 minutes, 10 or so minutes. So in chapter 7, remember, we have done chapter 4 and 5 in this structure. Chapter 4 and 5 were about a single regressor case, and chapter 4 was more of an introduction and estimation, how you estimate that model and how you interpret what assumptions are needed and what is the goodness of fit. That's our topics in chapter 4. And chapter 5 was statistic analysis of the single regressor regression case. So we learned hypothesis test, confidence interval, how we calculate the standard error, what is the sampling distribution, what is the t-statistic, and what is the p-value. Those are covered in chapter 5. So chapter 4 and chapter 5 are a pair. And now chapter 6 and 7 are another pair. So they both consider multiple regressor case, and chapter 6 was more about motivation, interpretation, and some basics. But chapter 7 is more serious statistical analysis, statistical inference, like hypothesis tests and calculating confidence interval. So this chapter 7 is actually quite different from chapter 5 because having more regressors generate more complicated problems. So we have much more things to consider. So let me start what we are going to do. So the names are look very difficult. Yes, they are difficult, but I'm not going deep in theory, but I'll try my best to give you the intuition why we are doing this and what we want to do and how we can extend the simple idea to multiple regressors. So if you understand single regressor case and the basic mechanism of hypothesis testing and confidence interval, then the extension is pretty straightforward. So don't worry too much about the theory. And today I'm going to only use graphs. I'll try to explain everything using some graphs. So just get the idea, the basic intuition. So now let's think about just a single coefficient beta 1. Suppose that there is only one estimate we are interested in. So in this real line, you have an OLS estimate beta hat 1. So there is a point. Suppose that it is a positive number. So you get an estimate of beta 1 from the data using the OLS method. This is what you get from Stata. So when you type regression command on Stata, you get a number which is a point on the real line. And on top of the point, we can calculate the margin of error. We have to admit that this estimation always has estimation error. Your estimator can be is always wrong, almost always wrong. The problem, it just what matters is whether whether it is wrong too much or the difference is little or large. Anyhow, so because there are errors, we need to calculate the standard error, which is literally the standard size of the error, and multiply 1.96. And then this is the standard margin of error. So you have to allow this much margin around the estimate if you admit there can be errors. So the errors may cover this much discrepancy. And then, so plus minus the margin of error makes an interval which we are going to call 95% confidence interval. 95 confidence interval, we call this 95% because this interval is accurate. This is correct with 95% probability. So like if you try 100 times, this interval will be wrong only 5 times. So in that sense, so this is standard 5%. Why is it 95%? It is your choice. You may use 99% or 90% or any other percentage, but the standard is 5%, 95%. So anyhow, 1 point, you get 1 point, but you have to think about the possibility of potential errors plus minus a certain amount, and then you get a confidence interval. And now, like in many cases, we would like to see if this estimate, this interval, contains 0 or not. Or it doesn't need to be 0. Sometimes it may be something different from 0. So you would like to compare whether the interval is includes or not a specific point. So let's say 0 in this case. So because 0 is not included in the interval, this means like with 95% probability, beta 1 is greater than 0. So anywhere on this confidence interval, your estimate is positive, always positive on the interval. So it is, we say that beta 1 is statistically significantly different from 0. So significantly different, but significance is a statistical term, so statistically significantly different from 0. And if you may choose a different number, like if 1 was here, then you can say that beta 1 is significantly different from 1. So if a point is not included in the interval, we can say that the difference is statistically significant. And or you may also say that statistically significantly positive. And in many cases, the most common case is 0, comparing with 0 to see the sign of beta, for example. So in this case, beta 1 is not 0. It does not, the interval does not include 0. So then when the reference point was 0, we say beta 1 is simply statistically significant. Different from 0 is not used, like hidden, so 0 is the standard. And also you have to put 5%. So you allow 5% error, and we only use the error probability. So how we read this result, how we say that, it's just convention. It is just tradition. I cannot change anything, change how we speak the language. So it's a statistical language. So you have to just follow this. There is no reason. There is no I cannot change anything. So this is how statisticians and researchers talk about this result. And if alternatively, so imagine the other case where the estimation was not that accurate. So like inaccurate estimation implies greater standard error. So greater standard error means you have to allow larger margin of errors. So then as a result, the interval will be wider. You have to allow larger margin. So the error interval will be wider. So at some point, 0 must be included in the interval. In this case, you don't know where the true beta 1 is within the interval. So the beta 1 can be any point on the interval. It can be 0, it can be negative, it can be positive. So the interval contains all the possible cases, negative, 0, positive. So in this case, beta 1 is statistically insignificant. You cannot distinguish whether true beta 1 is 0 or not, because there is one reasonable candidate, a strong candidate. So in this case, we say statistically insignificant. Okay, in one-dimensional case, like when you consider only one coefficient, one estimate, this analysis is pretty easy to understand because it is just one directional, like a one line, one-dimensional line. But now let's extend the idea to two dimensions. So suppose that you include another variable into your regression model, and you have two variables like student to teacher ratio and the percentage of English learners. And we would like to analyze two estimates at the same time, two coefficients at the same time, and then on OLS estimate, we'll be given a point on two-dimensional plane. So beta 1 dimension, beta 2 dimension. So beta 1 is estimated this point, beta 2 is estimated this point. And then jointly combining 2 points, we have this one point on two-dimensional plane. And okay, so it is not that difficult to understand the results. Like, so OLS estimates two coefficients. So you are going to have, like, say, some beta 1 comma beta 2 at a point. But then what is the confidence interval? Okay, we have standard errors for beta 1 and for beta 2. How can we utilize standard error for beta 1 and beta 2 at the same time? You may consider a box, a rectangle. The rectangle could be one possibility, like make a band here. So you can make a rectangle, but what we do is an ellipse. You cannot be an interval. It's two-dimensional, so interval is only on one dimension. But extending the concept of interval, we have an oval or ellipse. So this gray area is the 95% confidence ellipse, confidence region, confidence set, or you can simply call this confidence interval because the basic idea is the same. So this, how we calculate this, is not that straightforward. Like you don't need to calculate the area, but I will show you how to use Stata, what kind of commands you can use on Stata to do this. And once you obtain this gray circle ellipse, then you can say the same thing. Like here, this gray ellipse does not include 0. Origin is here, 0 point is here. So because the origin is not included in the ellipse, we say that beta 1 and beta 2 are jointly statistically significantly different from 0. So jointly is the point now. So in this case, we don't drop this part. So statistical significance is usually used only for a single estimate. Each of the estimate can be said to be statistically significant, but we don't say jointly statistically significant. But not wrong, but I have not heard much about that. Okay, that is what we are going to do in multiple regressor case. And we are going to start the main part in the next lecture next week. So have a nice weekend, and yeah, and my plan is I think I'm going to include this chapter 7 in the midterm exam. So I hope to finish chapter 7 in a week, and then the midterm exam coverage is 4 chapters, 4, 5, 6, 7. So two types of regressions. Okay, thank you for watching. See you later.